the expression C times the vector W1, W2, what is that C called? A scalar multiple, or you could also call it a weight, or just a scalar, that's fine. Scalar or scalar multiple, or a weight. What does it mean for a system to be called inconsistent? No solutions. And if you graph a system of linear equations that has no solutions, what will the lines look like? Parallel. Good. All right, so you guys wrote good questions. If you wrote a question, you get 1 point. You get 1 point for each of the questions you got right. And then you get 1 point if you took notes on the reading, for a maximum of 4 points. So next to your name, under your name, next to today's date, put your score out of 4 on the folders. Anyone have a question, homework, or anything from last class? Sure. Okay, so it's x2 plus 5x3 equals, oops, that's 11. Okay. So this is number 12 from your homework. We're just supposed to solve it. So we're going to use our algorithm to row reduce, use a matrix. Okay, so I asked if there were questions because we didn't quite get through the whole lesson. You didn't get through all the activities at the end of last class, so I thought it would be good to do one together before we start today's lesson. All right, so I put the x1 coefficients in the first column. So I've got 1, 2, -2. x2 coefficients are -5, -7, and 1. And x3 is 4, 3, 7. And then the numbers, the constants on the other side of the equal sign are -3, -2, -1. All right, so this is going to be equivalent to, you might see that symbol, I forgot to write that on the board at any point yesterday. That means row equivalent to. So I'm going to do some kind of row operation. And my first goal is that I want this entry and this entry. Well, my ultimate goal is for that entry, and that entry to all be zeros, right? Because I want to turn this into a triangular matrix. So the algorithm says work column by column from left to right to try to turn those 3 entries into zeros. So I'm just going to do the 2 first. I want to try to bump that 2 out of there. I would like it to be a 0, and I'm going to use row 1 to try to bump it. Okay, so what could I multiply row 1 by and add it to row 2 to make 0? -2. Okay. So I'm going to make a new row 2. Row 2 is the only row I'm changing right now. So I'm going to write down here row 2 is going to become row 2 plus a multiple of row 1. So -2, row 1. So the algorithm says that if to change a row by using replacement, any row is always just plain old itself plus a multiple of another row. So row 2 becomes row 2 plus -2, row 1. Everything else is going to stay the same, so I can just copy my entries from row 1 and row 3. So I have 1, -5, 4, -3, and -2, 1, 7, -1. Once you get faster at this and better at this, you might do two row changes in one step, but for now, just like write everything down, do one step at a time. All right, so if I multiply row 1 by -2, 1 times -2 is -2, plus the 2 gives me the 0 I'm looking for. Then -5 times -2 is 10, add that to the -7 and I get 3. 4 times -2 is -8, plus 3 is -5. And then -3 times -2 is 6, plus -2 is 4. Everybody see where that new second row comes from? If it's hard to do it in your head, just write down, write down row 2 becomes row 2 plus -2 row 1, and write everything out, add them together, just put it off to the side. All right, so what's my next goal? What do I want to get rid of next? The -2. Yep, so we work column by column, trying to create a triangular matrix. So my next goal is to get rid of this -2. And I'm going to use row 1 again to do it. Why wouldn't I use row 2 to knock it out? Because there's a 0 there, and no matter what you multiply 0 by, it's always going to stay at 0. So that's why we stick with row 1, to try to knock out everything below it. So I'm going to multiply row 1 by 2 this time. So my only row that's changing is row 3, so I'm just going to copy the other 2. And I'm going to write down, this is going to be, row 3 is going to change. It's going to be itself plus 2 row 1. So multiply row 1 by 2. 1 times 2 is 2, plus the -2 gives me the 0 that I was looking for. 2 times -5 is -10, plus 1 is -9. 2 times 4 is 8, plus 7 is 15. And 2 times -3 is -6, plus 1 is -7. All right, I'm almost there. What's my next goal? Get rid of the -9. Yeah. I want to get rid of that -9. So how could I get rid of it? Multiply row 2 by 3. Yeah. Yeah, algorithmically, often we might turn that 3 into a 1 by scaling that whole row. I'm not going to do it in this case because it's going to introduce fractions, and like, why bother, right? So this is going to become, row 3 is going to change. So it's going to be row 3 becomes itself plus 3 row 2. Okay, so row 3 is the only one that's changing. Copy the other 2 rows. 1, -5, 4, -3, 0, 3, -5, 4. Okay, my last row, I have to multiply row 2 by 3. 0 times 3 is 0. Add that to 0, you still have 0 in the first column, which is good because I want zeros there, and you don't want to make a move that's going to mess up your zeros that you already worked so hard to put there. All right, now 3 times 3 is 9 plus -9. That gives me the 0 I wanted. 3 times -5 is -15 plus 15 is 0. And then 3 times 4 is 12 plus -7 is 5. All right, so let's just translate this back to a system of equations. We've finished the algorithm. It's in triangular form because I have the zeros underneath the main diagonal, a lower triangle of zeros. So if I translate this back into Echelon, back into a system, This says x1 minus 5x2 plus 4x3 equals -3. 3x2 minus 5x3 equals 4. What does that last row translate to? 0 equals 5. 0x1 plus 0x2 plus 0x3 is 0 equals 5. Yeah, it don't make no sense. Yeah. 0 equals 5 is an untrue statement. So this system has no solutions. We call this an inconsistent system. Inconsistent / no solutions. That was a good one to ask about because we didn't get a chance to talk about inconsistent systems last class. Good. So we've reviewed the algorithm, talked about inconsistent systems. Let's look at today's lesson. All right, so today we're going to refine the algorithm that we've been developing and extend it. That's it. Okay, so last class we used the 3 elementary row operations to put a matrix into triangular form. That is, we made it so that we had zeros underneath the diagonal. In pursuit of that goal, you work column by column from left to right, using the nth row to eliminate all entries in the nth column that were below the nth row. That triangular form, the real word for that is called echelon form. So it turns out that this algorithm that we developed last class, it's sufficient for solving a system because once you get to triangular form, you can back substitute and finish solving the system. But it's actually only half of a complete algorithm, often referred to as Gaussian elimination, after the mathematician Gauss. So what we learned so far is just called the forward phase of the algorithm. Today we're going to learn the backward phase. And the goal of the backward phase, after we get it into echelon form, is to make all of the leading entries 1, and then to make each one the only non-zero entry in its column. So that's called reduced echelon form or row reduced echelon form or RREF. I'll call it RREF a lot for row reduced echelon form. To get row reduced echelon form, first you have to get it into echelon form. So do the thing we learned Tuesday. And then you work column by column again, but this time from right to left, eliminating everything above the pivots instead of below. So we'll do one together, and then I have a bunch for you to practice. All right, so first translate this to a matrix. So my x coefficients are 2, 0, 3. My y coefficients are 0, 1, 6. And my z coefficients are -6 to -2. Constants, -8, 3, -4. Okay, so my first goal is to get rid of that 3. Right? I would like that to be a 0. To make it a little easier for me to do that, I'm going to scale row 1 first. I'm going to make that first entry in row 1 a 1 instead of a 2. Just going to make things the arithmetic a little easier. So row 1 becomes 1/2 of row 1. Just scale the whole row. It's equivalent to multiplying both sides of the equation by a half. So this becomes 1, 0, -3, -4. Everything else stays the same. All right, now it's going to be easier to choose a number to multiply row 1 by to knock out the 3 in row 3. What should I multiply by? -3. Okay, so I'm going to replace row 3. Gets replaced with itself plus -3 row 1. So rows 1 and 2 aren't going to change. row 3 is going to change. So I'm going to do 3 times row 1, negative 3 times row 1, and add it to row 3. So 1 times negative 3 is negative 3, plus 3 from row 3 gives me the 0. Negative 3 times 0 is 0, plus 6 is 6. Negative 3 times negative 3 is 9, plus negative 2 is 7. And negative 3 times negative 4 is 12, plus negative 4 is 8. Okay, next goal is to get rid of that 6. You got it. Or I'll negative 6, yeah. So row 3 is going to change. That's the row I'm trying to change. So to change a row, you have to add itself to a multiple of another row. So it's going to be negative 6, row 2. So row 3 is changing, so I can just copy rows 1 and 2. So row 3, take negative 6, row 2, and add it. So negative 6 times 0 is still 0. Add that to the 0, still get 0. Negative 6 times 1 is negative 6, plus 6 is 0. That's what I was looking for. Negative 6 times 2 is negative 12, plus 7 is negative 5. Negative 6 times 3 is negative 18, plus 8 is negative 10. So I'm in triangular form now. This is sufficient to solve the system. I could translate these two equations and back substitute. So what is x3 here? 2. Yeah, you can easily finish solving here. This is called echelon form. Just so you know, you could stop here. But we're going to keep going and put this into row reduced echelon form, which you start by wanting to have 1s in all of your pivot positions. Okay, I already have a 1 here and here. I would like this to be a 1. What could I do? Divide by negative 5. Yeah, multiply by negative 1/5. Same thing. Scale row 3. Row 3 is going to be negative 1/5, row 3. Keep everything else the same. 1, 0, negative 3, negative 4, 0, 1, 2, 3. This is going to become 0, 0, 1, 2. So now I have 1s in all my pivot positions. Remember from your reading, a pivot position is just the leading entry of each row. Leading meaning the first non-zero entry of each row. They're all 1s. Now I'm going to work column by column from right to left, just on the coefficient part of the matrix. I don't care about the augmented part, which is the constants. Just on the coefficient part, I'm going to work right to left and try to eliminate everything above the pivots. I want them to all be zeros. So instead of just a lower triangular matrix, it's going to also be upper triangular. Everything zeros except for 1s in the pivots. Okay, work column by column, right to left. So if I want to get rid of that 2, what could I use to get rid of it? Row 3 by negative 2. You got it. So row 2 is going to change. So I have to add to row 2. So let's just be an arrow. Row 2 is going to be itself plus negative 2, row 3. Okay. And I want to use row 3 and not row 1, right? If there was a 1 there, you might be tempted to use row 1. But I don't. But I like that the row 3 has 2 zeros in it, so it's not going to mess up the work I've already done. All right, so row 2 is changing. I can copy everything else. Okay, row 2. Take negative 2 times row 3. So my first two entries aren't going to change. I've got 0 and 1, because -2 times 0 still gives you 0. And then -2 times 1 is -2, plus the 2 is 0. -2 times 2 is -4, plus 3 is -1. Next goal is to eliminate the -3. So we're working column by column. So we're still working on the rightmost column. I want all zeros above the pivot. So to get rid of that -3, you got it. R1 is going to change. So you're going to take R1 plus 3, row 3. So copy row 2 and 3. Okay, row 1, we're going to stay 0, 1, and then 3 times 1 is 3, plus -3 is 0. 3 times 2 is 6, plus -4 is 2. Oops, I had it right the first time. Supposed to be 1, 0, 0. All right, and then I would move to the next column to the left, and I want to make sure that I have zeros above the pivot, which I already do. Just happens to already be done. Now, if you translate this to a system of equations, this says x equals 2, y equals -1, z equals 2. So we've just folded that back substitution step into the algorithm with the matrix. And this last matrix we got, this is our REF, row reduced echelon form. What do you think? Slightly tedious, right? I'm going to make you do it by hand for another class or two, and then I'll show you how to get technology to do this for you. Okay. All right, so you can jump into the activities, work together or independently, I don't care. Call me over if you have a question.